Good morning, class. Welcome back. Let's quickly continue Module 5.2 of CHE 101 General Chemistry 1, Dissociation of Acids and Bases. We have looked at the theories behind acid-base reactions and acid-base chemistry. I hope you enjoyed this class. Welcome back. Outline of the lecture, we'll look at strength of acids and bases, look at Oswald's dilution law, ionization or dissociation of water, look at an illustration, and then we conclude. Strength of acids and bases. A strong acid easily loses proton and it's highly dissociated in solution. Now we're talking about strong and weak. Just like a strong man and a weak man. A strong man will beat you up and a weak man will run away. So beating up is equivalent to losing, because that is part of how we can classify the acid by loss of proton. So if it loses proton easily, then it's a strong acid. A weak acid, loses proton with difficulty. Just like I said, a weak man will run away. He's finding it difficult to go and fight, display strength because there's no strength. So a weak acid loses proton with difficulty and is slightly dissociated. Now let's look at this strong and weak acid. If we're talking about proton, the proton here is a hydrogen, and that is what gives us the acid strength. So if you look at H2SO4, the entire proton is giving off 2H plus here, plus SO4 2 minus. That's a strong acid. But look at a weak acid here. It loses only this hydrogen here, but there's still hydrogen here. This hydrogen here still has a little acidic character. Of course, when you come to second semester, when you'll be doing 102, you'll be looking at your inductive effect, mesomeric effect, hyperconjugative effect, which will lead to acid strength. Most of these weak acids are organic acids. Like this is acetic acid. Look at there's still hydrogen here, H3. It cannot lose this H3. It only loses this. If it were possible for this acetic acid to lose all this hydrogen and these 3 hydrogen here, then it becomes a strong acid. But it loses only one. Look at the one here. That's why it's a weak acid, because the acetate ion here still has some proton content here, which still makes it slightly acidic too. So that's why we say it's a weak acid. Also, a strong base easily or readily accepts proton and is highly ionized. Look at the strong base, potassium hydroxide. It's a strong base. Now, a weak base accepts proton with difficulty and is slightly dissociated. Look at it here. This is our weak base. Again, look at what's happening here. That makes ammonia hydroxide also a weak base. Therefore, by Bronsted and Lowry concept, the relative strength of a base is a measure of its ability to accept proton. Of course, that's what we said. This means that between two substances that compete for proton, the one that gains proton over the other is more basic. I hope we are understanding the argument. For example, water molecules can compete with Cl- for a proton, but Cl is a weak, very weak. Look at the equation. If you look at this equation, Cl is very weak as a base, and so weak that water easily accepts proton and forms hydrozonium ion. So Cl, assuming Cl is strong, it will not allow this hydrogen. Look at the argument. It's funny anyway, but then look at it critically. Water is stronger, so it collects this proton from Cl and leaves Cl as Cl minus. And when it collects this, it now forms hydrozonium ion. So that's a competition. For example, water molecules can compete with Cl minus ion for a proton, but Cl is very weak as a base, so weak that water easily accepts proton and forms hydrozonium ion. Again, on the other hand, water is eliminated, in the competition with ammonia. Look at it. Ammonia is competing with water. Ammonia now collects hydrogen. The same thing water did to Cl there. Ammonia now collects hydrogen from here and forms NH4. So you see, ammonia takes proton from water, forcing it to act as an acid. Water is strong enough to react almost completely with some proton donors, such as, so water can do that. The reaction of water with these acids can generally be represented as HA. Look at it, H, 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 H. So this A here will represent Br here, Cl here, NO3 here, ClO4 here. And of course, because we have HHA, this will all be 1 minus. This will be ClO4 minus, NO3 minus, Cl minus, Br minus. So that is this A minus here. A minus represents all these Br, Cl, NO3, and ClO4. So generally, this is a reaction. HA plus water will form this. As a result of this, it is not possible to distinguish the strength of these acids in aqueous solution like water. Can you imagine? So when in aqueous solution, water will always take this hydrogen from them. So it becomes easy for you now to say how strong all these acids are in the presence of water. In other words, the strongest acid can be measured. The strongest acid that can be measured in water is H3O plus, because water H2O will always collect hydrogen and form this. Substances which are better proton donors than H3O plus ion form this ion in water, and they appear to have the same strength. This is what we call leveling effect of water on acid strength. This is important. So water levels effect, levels the strength of all the acids as if they don't have strength again. In order to distinguish between the strength of acid, it is necessary to use some solvent that is a poorer proton acceptor than water. So we cannot use water anymore. We'll have to look for something else that can be used. And that's what we're heading to, towards dilution law. Now, strong acids and strong bases are strong electrolytes, while weak acids and weak bases are weak electrolytes. The conductivity of these aqueous solutions of weak acids and weak bases are very small. Now, low conductivity indicates that the reaction, that is dissociation, does not proceed to a very large extent. That is too small. Very few ions are furnished. So now consider this reaction AB, A plus B minus. This is a dissociation. Alpha is the degree of dissociation. Since we have 1:1 electrolyte here, 1 mole here, 1 mole here, 1 mole here, this will now give us, remember we met something like this in the solubility and solubility product, that is using the law of mass action. That's the same thing we're applying here. So we'll see this. Now the Ka, dissociation constant of this acid, will give us A with alpha over V divided by 1 minus alpha over V. If we solve that, we'll get this. So equation 3 and 4 are statements of Oswald's dilution law, which relates the dissociation constant Ka and degree of dissociation alpha of weak acids to the concentration. Now this law states that for binary electrolytes, look at it, Ka is equal to alpha squared C divided by 1 minus alpha. Of course, alpha is the degree of dissociation and C is the concentration. Remember the relationship between concentration and volume. C is equal to 1 over V, or V is equal to 1 over C. So if we replace C here by 1 over V, we arrive at alpha squared divided by V into 1 minus alpha. Now this law applies with a fair degree of accuracy to weak electrolytes, that's acid and bases, and it is named after Oswald. If Ka, the dissociation constant, is calculated for strong electrolyte, it is found that it varies considerably at different dilution. But for weak electrolyte, there is good agreement. For weak electrolytes, the degree of dissociation is very small. That is 1 minus alpha is approximately 1. Remember, the degree is very small, so we can Ignore this alpha. Since the dissociation is small and negligible, therefore we can say that for weak electrolytes, Ka is approximately alpha squared over V, which is approximately alpha squared C. Therefore, alpha will now make alpha the subject. Oswald's dilution law breaks down completely when applied to strong electrolytes. However, for weak electrolytes, we have ideal solutions similar to ideal gas behavior. Of course, for those of you who take a higher course, by next year we will explain this further. We'll look at the graph of conductivity against concentration. We'll start talking about molar conductivity at infinite dilution and so on, applying all these equations we have here. But for now, we just want you to have the elementary knowledge of this. Ionization or dissociation of water. So back to water again, look at it. Let's move a little faster. Look at the water now. Very poor water. This is water ionization. If we have two molecules, we form hydrozonium ion and OH. If it's one molecule, both equation 7 and 8 are the same. And we'll call this self-ionization or auto-ionization of water or self-protolysis. Applying the law of chemical equilibrium to equation 7, we're just using, so if we use equation 8, we'll get the same thing. We have K equal to concentration of the products divided by concentration of the reactant squared, because there is 2 here, remember. So if we cross multiply, this concentration of water squared multiplied by K is this, then this is the numerator, hydrozonium multiplied by this is equal to constant. Therefore, hydrogen ion concentration, OH ion concentration is equal to Kw. Now remember, this is exactly what we did in solubility, and we got solubility product. In fact, if it were to be in solubility product, this Kw will be Ksp. Go back and check. This will be Ksp. That's exactly the same thing we did for any sparingly soluble electrolyte. In this case, we are looking at water. So which means H plus if we're using equation 8, or hydrozonium ion if we're using equation 7. They are the same thing. 10A and 10B are the same. Where Kw is called the ionization constant of water or dissociation constant of water. This is very important. We'll see where we apply it. We can see that for a moderately dilute solution, it is equal to a constant at 25 degrees C, which is equal to 1 times 10 to the power minus 14. That is, OH minus concentration and H plus concentration is equal to 10 to the power 7, 10 to the power 7, which is equal to 10 to the power 14. The same way, OH minus and hydrozonium ion concentration is equal to 10 to the power 7, 10 to the power 7, equal to 1 times 10 to the power minus 14. Obviously, when we add acid to this solution, the concentration of hydrogen ion or hydrozonium ion will be more than this. It will increase. To maintain this constant Kw, the concentration of hydroxyl ion will fall. I hope you understand that. Because concentration of this is minus 7, which is equal to minus 14. So if this one increases, this one must reduce for it to be equal to this. The same way, if we add a base, the one for the base will increase. Therefore, this will also reduce to be equal to this. So if we add a base, the concentration of hydroxyl ion will be greater than this, 10 to minus 7 to be greater. And concentration of hydrogen will be less, reduced. In a neutral solution, the concentration of hydrogen ion is equal to 1 times 10 to the power 7. This is one way of expressing the hydrogen ion or hydrozonium ion concentration. Another way of expressing hydrogen ion, hydrozonium ion concentration is the pH. To look at an illustration, we use an illustration for our Oswald's dilution law. The ionization or dissociation constant of benzoic acid is this. What is the degree of ionization or dissociation of this acid in 0.2 molar solution? And what are the concentration of hydrogen ion and benzoate ion at this of this acid? Look at it. This is the dissociation. We'll apply our equation again, substitute alpha 1 minus alpha. Since benzoic acid is weak electrolyte, alpha is very small. So 1 minus alpha is equal to 1. So this is equal to that. We'll get alpha as this if we solve. Then the concentrations will give us alpha C. Remember, this is alpha over V. C is equal to 1 over V. So this is the same as alpha C, and which is this. All right. Thank you very much. We've come to the end of module 5.2. And this is a very sweet lecture. I hope you're going to enjoy it. I hope you enjoyed the class. We looked at strength of acids and bases, Oswald's dilution law, ionization or dissociation of water, and then looked at illustration. Thank you very much and hope to see you in the next class, module 5.3.